In this video, we're going to learn how to write a proof by cases. First, we're going to do an example, and then I will tell you why it works. Imagine that we want to prove this theorem, that if n is an integer, then n squared plus n is an even number. Well, if we just start with an arbitrary integer, I don't have much to work with, and it's going to be very difficult to go from there to the fact that n squared plus n has to be even. But there are some things that I know about integers that I can use to my advantage. And a very useful fact is that an integer must be either an even or an odd number. And those are the only two possibilities. So what we can do is we can split this problem into two sub-problems by considering two cases. We can consider the case when n is even and the case when n is odd separately, so we have two more manageable problems, and then we put everything back together to conclude about all the integer numbers because, well, we've covered all the possibilities. So the way we do it by cases, as I said, we're going to split it in two cases, and now for the case n is even, well, we have a sub-proposition. That is that if n is even, then n squared plus n is even. And I would prove this. Now, if I know that n is even, then I know that there exists an integer m such that n is equal to 2m. And now I have something to work with. So, well, if n is equal to 2m, then n squared plus n would be 2m squared plus 2m. But that is 4m squared plus 2m, so I can take a common factor 2, and then we have that n squared plus n is equal to 2 times 2m squared plus m. But, well, we know that 2m squared plus m is an integer. Then with this, I can conclude, indeed, that n squared plus n is even. And now I need to do the same thing for the case when n is odd. Well, if n is odd, now I have this sub-proposition that if n is odd, then n squared plus n is even. And again, now we're going to use the definition of odd number to help us out here, so we have something to expand, something that we can manipulate. So if n is odd, there is an integer k such that n is equal to 2k plus 1. So now if I plug this into n squared plus n, well, we'll have that n squared plus n is 2k plus 1 squared plus 2k plus 1. Now we need to expand this squared. Will gives us that we have a 4k squared plus 4k plus 1 plus 2k plus 1. And then, well, we perform the additions to simplify things a little bit. And then we have that this is 4k squared plus 6k plus 2. And again, we can take a 2 common factor. So we have that this is 2 times 2k squared plus 3k plus 1. And the thing inside the parenthesis is again an integer number, which is great because then I can also conclude in this case that n squared plus n is even. So this is the idea of the proof, and now I want to put it nicely into one cohesive proof where the reader knows exactly what I'm doing. Well, we start again with the statement of our theorem. If n is an integer, then n squared plus n is an even integer. And the first thing that we're going to do is we fixed an arbitrary integer. And now we're going to tell the reader that we want to do a proof by cases. So, well, we'll tell them that we're going to prove that n squared plus n is even by examining the case where n is even and the case when n is odd. And we do the first case. Well, let n be an even integer, then there is an m in z such that n is equal to 2m. And here we perform the algebra, exactly the same thing that we did before. And now, well, since we know that the set of integers is closed under addition and multiplication, then we know that 2m squared plus m is an integer. So if we now define p to be 2m squared plus m, we know that this is an integer, and I know that n squared plus n is equal to 2p. Oh, brilliant! That tells me that then n squared plus n is an even number. And now we have to do case 2. I fix n to be an arbitrary odd integer. We're assuming that we started with an arbitrary integer and now we're taking 2 cases. So now we're going to look at the case that n is odd. Now we know that there exists an integer k such that n is equal to 2k plus 1. And we're going to again perform the algebra the same as we did before. So I'm not going to go over it again. But well, now we know again that the set of integers is closed under addition and multiplication. So 2k squared plus 3k plus 1 is an integer. And if I define q to be 2k squared plus 3k plus 1, this is an integer, and n squared plus n is indeed 2 times q. So by definition of an even number, I know that n squared plus n is even. And now, remember, those are the only 2 options. Given an integer, the number is either even or odd. There is no other option. So no matter which integer I pick, I managed to prove that in either case, n squared plus n is an integer. And that completes my proof. Now, why does this work? Well, let's see. This works because you see the statement P or Q implies R is equivalent to the statement P implies R and Q implies R. So if you're curious about why this works, I invite you to check this using truth tables, as you've already learned before. Now, some things that are very important to keep in mind. We need to make sure that each possibility is included in your reasoning. If you do a proof by cases and you forget one of the options, then your proof will fail. Maybe that was the case that makes the whole thing to not be true. So we need to always make sure that we're covering all the possibilities. And we need to also split the problem wisely. Whenever you're given a question, try to think of how we can split it in a way that works to your advantage. Something that is going to give you things that are manageable, that make your life easier and not more difficult. Some common uses of cases in proofs are, well, when the hypothesis n is an integer, a very common thing to do is to split it into evens and odds, like what we just did. But there are many different ways depending on your ultimate goal. Now, when the hypothesis x is a real number, you could split it in many different ways, but some of the most common ones are rationals and irrationals, 0 and not 0, or 0, positive and negative, but there are infinitely many different ways to split the real numbers to have different cases. How we choose the cases we want? Well, that will be given by our problem. We need to split it in a way that is going to help us solve the problem. We're going to see in a future video an example on where we have to split the real numbers into a different way, because that is what is going to be most suited for a proof. Now, for us, most of the times we're going to use proofs involving 2, 3, maybe 4 cases, but usually no more. But there is actually no an upper limit on the number of cases that you consider in a proof by cases. So for example, the first proof of the 4-coloring theorem uses 1,936 cases. That is a lot of cases.